Currently, every galaxy existing in the boundless expanse of the cosmos is steadily moving away from us at truly astonishing speeds. The farther a galaxy is located, the faster its movement away from our observation point, with some rushing at speeds exceeding 600,000 miles per hour. However, this is precisely where the true mystery begins. For, contrary to intuitive understanding, these galaxies are not actually moving through space. Instead, space itself is stretching, carrying all objects along with it, much like points on the surface of a balloon move apart as it inflates. In our journey, we will visit the cosmic microwave background radiation, directly witness how the mysterious dark energy is tearing apart the very fabric of existence, and confront the astonishing possibility that our universe has no edge, no outside, and consequently, no end. Get ready, we begin. In 1929, a humble astronomer named Edwin Hubble, pointing his telescope at distant star clusters, made a discovery that forever changed our understanding of reality. Hubble noticed that almost every galaxy he observed was moving away from us. However, this movement was not chaotic or random. On the contrary, there was a flawless, almost mathematically precise pattern. Galaxies twice as far away moved twice as fast. Those 3 times farther moved 3 times faster. It seemed as if the entire universe was participating in some grand cosmic choreography that we had never before noticed. Imagine standing in the middle of a vast crowd, and everyone simultaneously begins to move away from you. But in this cosmic crowd, those farther away are not just walking, they are running. And the people at the farthest reaches are rushing at such incredible speeds that they are practically flying. Hubble was able to measure this phenomenon using an effect known as redshift. When light travels from a moving source, it either stretches or compresses, similar to the change in pitch of a passing ambulance siren. Light from galaxies moving away from us is stretched, shifting to longer, redder wavelengths. The faster they move, the redder they appear. Some galaxies were so redshifted that their light had stretched almost twofold compared to its original wavelength. This astounding discovery demonstrated that space itself is actively growing. Every cubic inch of seemingly empty space was slowly expanding, pushing galaxies apart, much like raisins spread out in rising bread dough. The universe, contrary to popular belief, was not static and eternal. It proved to be dynamic, growing and evolving with every passing second. However, Hubble's discovery raised a question that plagued physicists for decades. If the universe is expanding, what exactly is it expanding into? The answer to this question challenged everything we thought we knew about space, time, and reality itself. What we discovered next would make Hubble's revelation seem relatively simple. The word expanding inadvertently makes our brains imagine the universe as a balloon growing larger inside a room. This comparison seems natural, as any expansion we encounter in everyday life occurs within something larger. A balloon expands into the air around it. A city grows, taking over the surrounding countryside. Even an explosion expands into space that already existed before it. Our minds automatically search for the room that contains our expanding universe. But cosmic expansion functions entirely differently. The universe is not growing into pre-existing space because no such pre-existing space exists. Space itself is expanding. This can be compared to an imaginary balloon that creates new space around itself as it inflates, without any walls or boundaries to exert pressure against. Imagine a sheet of graph paper with individual dots placed on it. Now imagine that the paper itself begins to stretch, and each of its squares becomes significantly larger. The dots naturally move apart, but it's important to understand that they are not moving across the paper's surface on their own. They are carried apart by the paper itself, which is increasing in size directly beneath them. This image is much closer to what is happening in our constantly expanding universe. This stretching of space encompasses everything around us and occurs simultaneously. For example, between Earth and its natural satellite, the Moon, space expands by about 1.5 inches annually. If we consider the gap between our solar system and its nearest star, That distance increases by thousands of miles per year. And between distant galaxies, space expands at such an incredible rate that it causes them to rush apart at colossal speeds. And here's what's particularly striking. This cosmic expansion has no center and no edge. Every point in boundless space perceives all other points moving away from it. For example, a hypothetical alien inhabiting a galaxy billions of light-years away from us would observe us moving away from them at the same speed at which we, in turn, see them moving away from us. This expansion looks absolutely identical from any point in the universe. Cosmologists call this phenomenon the cosmological principle. Regardless of your location in the universe, the overall picture will always be roughly identical. You are not at the center of the expansion, as no center simply exists. Nor are you close to the edge, for the universe has no edge either. But if space itself is expanding, and there is neither an edge nor a center, then a natural question arises. What lies beyond everything we are capable of observing? The balloon analogy, widely used to explain the phenomenon of cosmic expansion, actually exacerbates rather than clarifies this profound mystery. When teachers inflate a balloon to demonstrate how galaxies move apart, they inadvertently embed a misconception in the minds of their listeners. Students, observing the balloon grow in volume right in the classroom air, conclude, "Ah, so the universe must also be expanding into some cosmic air." But this misses the most crucial aspect. The balloon example only works correctly if you completely ignore everything outside the surface of the balloon itself. Imagine yourself as an ant living on the surface of this balloon. Your entire world is confined to the rubber skin. You can move north, south, east, or west across this surface, but you cannot move up or down into the air surrounding the balloon. These directions simply do not exist in your two-dimensional world. As the balloon inflates, your world gets bigger, but you have nothing to worry about, as no outside exists for you. Now take this concept and add another dimension to it. We live in a three-dimensional space that can expand in the same way as the ant's two-dimensional surface. Just as the ant cannot leave the balloon and enter the surrounding air, we cannot leave our three-dimensional universe and enter some fourth spatial dimension. The key idea is that expansion does not require an outside. The surface of a balloon can increase without expanding into anything from the ant's perspective. The surface simply begins to have a larger area than before. Similarly, our universe can contain more space than before without requiring that space to come from somewhere. This brings about a profound shift in our thinking. Instead of asking what the universe is expanding into, we should be asking how space itself is changing. The universe is not moving through some larger container. It is the container itself, and that container is constantly increasing in size. But this raises an even deeper question. If space itself is expanding, what does that mean for the nature of space and time? Space is not an empty nothingness waiting to be filled. It is a physical entity with certain properties, and these properties are undergoing change. Most people are accustomed to thinking of space as a stage upon which all physical processes unfold. Planets orbit, light propagates, and forces act against this invisible backdrop we call space. However, Albert Einstein showed us that space is much more like an actor in this cosmic drama. It curves around objects with mass, it vibrates with external disturbances, and yes, it expands over time. Imagine cosmic space as a flexible, stretchable fabric. When you apply force to a rubber band, you're not adding new material. You're simply redistributing the existing material over a larger area. As a result, the fabric becomes thinner and less dense, but it covers a significantly larger territory. The expansion of space functions on a similar principle, with the only difference being that instead of thinning, it retains its original properties, simply providing significantly more room. This is where truly astonishing phenomena begin. New space is continuously emerging. Every second, approximately 1 cubic foot of new space appears between our planet Earth and its natural satellite, the Moon. Annually, about 15 billion cubic miles of new space materializes between our galaxy and its nearest galaxy. It is important to emphasize that this is not empty space moving from somewhere else. This is truly newly created space, arising literally from nothingness. This amazing creation occurs at a rate that is directly dependent on distance. Objects located close to each other barely notice this expansion, as gravity and other fundamental forces easily overcome it. Your body does not expand. Your home does not expand. Even Earth's orbit does not increase in size. However, on colossal cosmic scales, where distances are measured in millions of light-years, expansion becomes the dominant force determining the dynamics of the universe. The speed of this expansion reveals something truly remarkable to us. Space is created at a rate of about 70 kilometers per second per megaparsec. This means that for every 3.25 million light-years of distance, space expands fast enough to separate objects at a speed of 70 kilometers per second. Double the distance, and you double the speed. But if cosmic space is a physical entity capable of expansion, what exactly is undergoing this expansion? The afterglow of the moment of creation itself still fills every corner of our universe, and right now it is stretching precisely because of this expansion. Approximately 380,000 years after the grand event known as the Big Bang, the universe had cooled sufficiently for the first atoms to form. Prior to this moment, space was filled with hot, glowing plasma, which prevented light from traveling significant distances. But when atoms finally formed, light was able to propagate freely throughout the universe. This very first light, known as the cosmic microwave background radiation, continues its journey through space to this day. Imagine a situation where a camera flash goes off in a room filled with thick fog. The light scatters and reflects, not reaching your eyes clearly. But if the fog suddenly disperses, you immediately see that flash illuminating everything around. The cosmic microwave background radiation is like this moment of clarification, frozen in time and stretched by billions of years of cosmic expansion. When this ancient light first began its journey, it was hot and bright, emitting light at a temperature of about 3,000 degrees Celsius. But as space expanded, the light waves stretched with it. Light that was originally in the visible orange and red ranges stretched into the infrared spectrum, then into microwave, and after that, into radio waves. Today, the same light has a temperature of only 2.7 degrees above absolute zero. We are able to detect this ancient light coming to us from all directions of the celestial sphere. It possesses astonishing uniformity, varying by only about 100,000th from one direction to another. This striking uniformity indicates to us that the early universe was incredibly smooth, and that expansion occurred uniformly in all directions. The cosmic microwave background radiation provides us with a kind of baby picture of the universe when it was only 380,000 years old. But what is even more significant is that it vividly demonstrates expansion in action. Every microwave photon we detect today once had a much shorter wavelength, which has been stretched by 13.8 billion years of cosmic expansion. However, measurements of this ancient light revealed something completely unexpected regarding the rate of expansion. It turns out that the universe is expanding at different rates depending on where you look. And this profound contradiction is driving modern physicists to the brink of madness. When the rate of expansion is measured using data from nearby galaxies, one result is obtained. If the cosmic microwave background radiation is used for these measurements, a completely different answer is revealed. Theoretically, these two methods should show perfect agreement, but in practice, this does not happen. This situation is comparable to trying to measure the same table with two different rulers and getting different lengths. Using observations of nearby galaxies, astronomers determine the expansion rate to be approximately 73 kilometers per second per megaparsec. This means that for every 3.25 million light-years of distance, cosmic space expands at such a rate that objects move away from each other at a speed of 73 kilometers per second. However, using cosmic microwave background data, physicists calculate an expansion rate of approximately 67 kilometers per second per megaparsec. A difference of 6 kilometers per second may seem insignificant, but in the context of cosmology, this discrepancy is quite substantial. This situation is analogous to finding that your car's speedometer and GPS readings do not match your current speed. In such a case, either one of the measuring instruments is faulty, or fundamental changes are occurring in the road itself. This discrepancy has been named the Hubble tension. This phenomenon suggests that either our understanding of the early universe is flawed, or our measurements of nearby galaxies are inaccurate, or something in the expansion process itself has changed over time. Some physicists lean towards the idea that dark energy is evolving. Others suggest the existence of unknown particles or forces that influence the expansion process. The tension intensifies as measurements become more precise. Instead of converging to a single value, both methods demonstrate different results with increasing confidence. It seems as if the universe is telling us two dissimilar stories about its own expansion, and we are unable to determine which one is true. This mystery points to something profound. The expansion of space may not be as simple as we assumed. Every search for the edge of the universe leads to the same maddening conclusion: it simply does not exist. The human mind is programmed to think in terms of boundaries. Every room has its walls. Every state has clear borders. Every lake has shores. We instinctively assume that the universe must have an edge somewhere, some cosmic boundary where space simply ends and something entirely different begins. However, decades of research have demonstrated that no such edge exists. Imagine what such an edge would actually look like. Imagine traveling in a straight line through space for billions of years, passing countless galaxies and stars. Eventually, you would expect to reach a place where galaxies become rarer, then very rare, and then disappear altogether. Beyond that, you would find empty space. And what beyond that? A wall? A void? A sign saying, "Universe ends here." The problem is that observations show the universe looks roughly the same in all directions, no matter how far we look into it. Galaxies are distributed uniformly throughout space, right up to the limits of our vision. There is no thinning out, no approaching edge, not the slightest hint that we are near any boundary. This does not mean that the universe is infinite, although that possibility is not excluded. It can be finite yet boundless, like the surface of a sphere. An ant moving on a basketball will never find an edge, even though the surface area of the ball is finite. The ant could walk forever in a straight line and never reach a boundary or return to its steps. Similarly, our three-dimensional universe may curve in on itself in ways we cannot visualize. You could travel in a straight line for billions of years and eventually return to your starting point, never encountering an edge. The universe would be finite in size but boundless. However, if it has no edges, then what defines the limits of all existence? The universe can be both finite and boundless simultaneously, which violates all the fundamental rules of logic we learned in school. This apparent paradox becomes absolutely clear when we begin to reflect on the distinction between the concepts of infinite and boundless. An infinite universe is presumed to stretch forever, in all possible directions, containing an innumerable amount of space and matter. A boundless universe, while having neither edges nor clear boundaries, can nevertheless possess a finite, measurable size. These are two completely different concepts that our human brain tends to confuse, perceiving them as one and the same. Imagine yourself standing on the surface of planet Earth. You can move freely in any direction for as long as you wish, and you will never encounter a physical wall or fall off a cliff. The surface of our planet is boundless, yet it is not infinite. It possesses a definite, precisely measurable area. Theoretically, you could circumnavigate the entire planet and eventually return to the exact point where you began your journey. Now, imagine this same principle applied to the entire three-dimensional universe. Space, in such a case, could curve in on itself in ways that are absolutely impossible for our consciousness to visualize. Yet they remain mathematically consistent and logical. Just as the Earth's surface represents a two-dimensional space curved through a third dimension, our three-dimensional universe could very well be curved through a fourth spatial dimension that we, unfortunately, cannot directly perceive. In such a universe, traveling in a straight line would eventually and inevitably bring you back to where you started. Such a universe would contain a finite amount of space and matter, but it would have no boundaries. There would be no edge to reach, no outside to expand into, and no center to find. This profound concept challenges our most cherished intuitive notions about space and reality itself. We are accustomed to expecting boundaries because our daily lives unfold in a world filled with walls and fences. However, on the vast cosmic scale, these familiar concepts completely break down. The universe operates by rules that seem utterly impossible until we realize that our everyday experience is merely a tiny slice of a much stranger and more wondrous reality. But this, of course, raises one of the most important questions. If the universe has no outside, then what does the concept of outside even mean? The word outside completely loses all meaning when applied to the totality of everything that exists. We typically use the word outside to describe relationships between different objects and phenomena within our universe. You can go outside your house into the yard, from the yard to the street, from the city to the countryside. But all these outsides are still within the universe. These are merely larger containers within the ultimate container of space and time. When we ask what the universe is expanding into, we are unconsciously trying to apply these inside-outside relationships to the universe itself. However, the universe is not just some object within a larger space. It is space itself. It is not expanding into something else because there is no something else. The universe is the complete set of everything that exists, and everything cannot have an outside. Consider this by asking yourself, what is north of the North Pole? This question seems perfectly reasonable until you realize that the concept of north only makes sense in the context of our planet Earth's geography. Once you reach the North Pole, you physically cannot move further north. The concept simply breaks down at that point. Similarly, the concept of outside only makes sense within the context of space, but space itself defines the boundaries of meaningful questions. This gives rise to what philosophers call a category error. We are trying to apply concepts that work perfectly well within the universe to the universe as a whole. It's like asking what color the number 7 is, or how much the universe weighs. These questions sound perfectly sensible, but they completely fall apart upon closer examination. The expansion of space does not require an outside because expansion is an inherent property of space itself, not a relationship between space and something else. Space can contain a larger volume than before without needing to displace anything or move into any pre-existing territory. But if there is no external space to expand into, how do we comprehend the phenomenon of expansion itself? The expansion of space affects colossal cosmic distances, while absolutely not affecting everyday distances. At this very moment, as a person is immersed in reading these lines, the space between distant galaxies is rapidly increasing. However, the space between the words on this page is not expanding. The space separating atoms in the body also remains unchanged. Even the distance between Earth and the Moon hardly changes. Expansion dominates exclusively on the grandest scales, where distances are measured in millions of light years. This is because expansion has to compete with other forces. Gravity holds atoms together. Electromagnetic forces bind molecules. And even on vast scales, gravity maintains the integrity of solar systems and galaxies. Expansion wins this competition only when objects are so far apart that gravitational influence becomes negligible. Imagine trying to stretch a rubber sheet to which coins are glued. The sheet easily stretches in the gaps between the coins, but the coins themselves do not change in size. The glue holding each coin is stronger than the stretching force. Similarly, the forces that bind matter together overcome expansion on small scales. This forms a cosmic hierarchy of scales. At the atomic level, expansion has no significance. At the solar system level, expansion can be detected, but its influence is minor. At the galaxy cluster level, expansion becomes noticeable. At the supercluster level, expansion dominates all other forces. The boundary between these scales is constantly shifting. As the universe expands and matter disperses, gravity weakens, and expansion begins to affect increasingly larger structures. Galaxy clusters that are barely held together today will eventually be torn apart by expansion. The universe is gradually succumbing more and more to expansion as time progresses. This process carries profound implications for the future of all existence in the universe. Dark energy is tearing the fabric of space faster and faster each day, and we have no idea what its nature is. In the late 1990s, astronomers anticipated discovering that the universe's expansion was slowing down. After all, gravity should have been pulling everything back together, counteracting the expansion, much like a ball thrown upwards fights Earth's gravity. But when they measured distant supernovae, they found something astonishing. The expansion is accelerating. Something is actively pushing space apart, overcoming gravity on cosmic scales. This mysterious force accounts for approximately 68% of all energy in the universe. Yet, we cannot see it, feel it, or directly detect it. We know of its existence solely through its effect on expansion. Scientists call it dark energy, but that is merely a name for our ignorance. Dark energy does not clump together like matter. It is uniformly distributed throughout space, maintaining the same density even as space expands. This means that as the universe grows, the total amount of dark energy increases. It is as if empty space itself possesses an intrinsic energy that drives the expansion. Imagine dark energy as a spring that grows stronger as it stretches. The more space expands, the more dark energy there is, and the faster the expansion occurs. This creates a self-sustaining process where expansion fuels itself, accelerating faster and faster over time. The acceleration is imperceptible on human timescales, but profoundly significant on cosmic ones. Galaxies that are currently moving away from us at 10% the speed of light will eventually move away at 50% the speed of light, then 90%, approaching the speed of light itself. The universe is heading towards a future where distant galaxies will vanish beyond the observational horizon. The observable universe is merely a tiny, limited bubble surrounding us, beyond which stretches a boundless, inexhaustible ocean of cosmic space, forever remaining inaccessible to our gaze. This phenomenon is explained by a fundamental property of light, its finite speed of propagation. It is for this reason that we can only perceive those cosmic bodies whose light has managed to travel the immense distance and reach us since the grand event known as the Big Bang. This circumstance forms a kind of spherical boundary around us, which scientists have named the observable universe. Its radius, according to modern calculations, is approximately 46 billion light-years, and it includes absolutely everything that we can potentially observe with existing technologies. However, it is highly probable that the actual universe significantly surpasses this limited observable bubble in size. To illustrate, imagine the following metaphor. A person stands in the middle of a boundless ocean in pitch-black night, holding a flashlight. The beam of light from the flashlight illuminates only a small circle around them. Meanwhile, the ocean itself extends far beyond this illuminated area, remaining invisible. Similarly, our observable universe is merely that region of space that light has had time to illuminate since its inception. Beyond this observable horizon lies even more space, even more galaxies, even more stars, and all of them are subject to the same universal laws of physics. But alas, they will forever remain hidden from our direct view. These distant regions are moving away from us at incredible speeds, exceeding the speed of light, thereby creating an insurmountable cosmic horizon that we can never cross. This can be compared to trying to swim to a distant island while a powerful ocean current continuously carries you back faster than you can move forward. This means that the universe we carefully study and analyze is merely a small sample, a specimen of a much larger and more complex reality. We are like scientists who try to comprehend the entire vastness and depth of the ocean by studying just a single drop of water. This drop, of course, can tell us about the ocean's chemical composition, but it is utterly incapable of revealing its true size or shape. The continuous expansion of space itself continuously pushes new regions beyond our observable horizon. Galaxies located at the very edge of our vision gradually disappear, carried away by expanding space faster than light can propagate. Thus, the observable universe actually shrinks in terms of the number of galaxies we are able to see and study. However, this circumstance raises the deepest and most fundamental question about the very nature of space. Every photon of light traveling through expanding space undergoes stretching, much like taffy stretches, and thus it reveals to us the entire history of cosmic expansion. When light travels colossal distances, it transforms into a kind of time machine, carrying invaluable information about the rate of expansion throughout cosmic history. Light emanating from nearby galaxies allows us to understand how space expanded in the recent past. At the same time, light from distant galaxies reveals a picture of how space expanded billions of years ago. By comparing these measurements, we gain a unique opportunity to trace how expansion has changed over time. As light travels through expanding space, its wavelength stretches proportionally to this expansion. Light that was originally blue gradually becomes green, then yellow, then red, then infrared, and finally transforms into radio waves. The magnitude of this stretching indicates with striking accuracy how much space has expanded since the light began its journey. Moreover, this stretching affects not only color, it impacts the energy of light, the speed at which we receive it, and even the apparent brightness of distant cosmic objects. A supernova exploding in a distant galaxy appears dimmer to us not only because of the immense distance separating it from us, but also because the expansion of space has stretched its light to lower energies and distributed its photons over a significantly longer period of time. This stretching is cumulative. Light that travels for 10 billion years is stretched by 10 billion years of expansion. Light that travels for 12 billion years is stretched by 12 billion years of expansion. This creates a unique cosmic timeline that is recorded in the wavelengths of light reaching us from various distances. By studying this complex timeline, astronomers have been able to reconstruct the complete history of cosmic expansion. They discovered that expansion slowed down during the first few billion years after the Big Bang, and then began to accelerate approximately 5 billion years ago, when dark energy became the dominant force in the universe. However, this grand cosmic saga reveals very alarming omens regarding the ultimate fate of the universe's expansion. The accelerating expansion of cosmic space inevitably pushes our universe towards a cold, dark, and absolutely empty future. As the mysterious dark energy drives this expansion with increasing rapidity, the universe enters a phase that will radically change all our understanding of cosmic evolution. Galaxies that are currently observable will gradually disappear beyond the horizon of visibility. Stars, like fading candles, will go out, lacking new material for their rebirth. The universe will steadily become colder, darker, and lifeless. This inevitable process has already begun. The rate of star formation in the universe peaked approximately 10 billion years ago and has since shown a steady decline. As expansion separates galaxies, they lose the ability to merge and thus to trigger new bursts of star formation. The universe is gradually depleting the raw materials needed to create new stars. In approximately 1 trillion years, the last stars will finally burn out. The universe will be populated only by brown dwarfs, white dwarfs, neutron stars, and black holes. These cosmic remnants will orbit each other in ever-expanding spirals as expansion relentlessly pulls them apart. Eventually, even these bound systems will be torn apart by the relentless growth of space. The ultimate fate of the universe depends on the fundamental nature of dark energy. If dark energy maintains its current properties, expansion will continue forever, creating a universe that becomes exponentially larger and emptier with each passing moment. If, however, dark energy changes, the universe could face entirely different fates, perhaps even a reversal of expansion that would bring everything back together. But regardless of its ultimate fate, the expansion of space has already irreversibly transformed the universe. We live in a brief cosmic moment when galaxies are visible, stars are actively forming, and the universe is abundant with structure and complexity. This grand transformation forces us to confront the deepest questions about existence itself. The expansion of space challenges our most fundamental assumptions about the nature of being, time, and reality. Everything we know about cause and effect is based on the idea that events occur within a stable framework of space and time. But if space itself is expanding, then these frameworks are constantly changing. The stage on which the entire cosmic drama unfolds is itself an active participant in the performance, growing and evolving with every passing moment. This gives rise to paradoxes that test our understanding. If space expands, then the distance between any 2 points is constantly increasing. But distance should be a fixed relationship between objects. If space is created, then the total amount of space in the universe increases. But where does this new space come from? These questions reveal the limitations of thinking about space as a static container. We are accustomed to thinking of space as a box that contains everything. But expansion convincingly demonstrates to us that space is more like a living, growing entity. It possesses its own properties. It can change and actively participates in the cosmic evolution it contains. The expansion of space also challenges our intuitive notions of infinity. If the universe is infinite, then it contains an infinite amount of matter and energy. But if it is expanding, then in the future it will contain an even greater infinite amount of matter and energy. This suggests that there are different sizes of infinity, and that infinity itself can grow. Perhaps most unsettling is the realization that expansion makes the universe fundamentally indefinite. We can never know how big the universe truly is, what lies beyond our observable horizon, or whether our local region is representative of the whole. The expansion of space has made the universe not just physically larger, but epistemologically unknowable. These profound philosophical implications point to even more fundamental mysteries concerning the essence of reality itself, its structure, and the limits of our knowledge. If the universe is currently continuously expanding, then mentally rewinding time inevitably leads to the moment when all space was compressed into a single, infinitely dense point. This is a logical consequence of the observed expansion, known to us as the Big Bang, which became the starting point for all existence. Since space is increasing in volume now, this means that in the past it was inevitably significantly smaller. If we continue to mentally rewind the timeline, we will eventually reach that critical moment when all the space that constitutes our universe was compressed into a region smaller than an atom. It is important to understand that this was not an ordinary explosion that occurred within already existing space. This was truly the explosive beginning of space itself, its birth. The Big Bang was not an event that happened in a specific place or point. It happened everywhere at once, because at that initial moment, everywhere was the same single place, indistinguishable and indivisible. Every cubic inch of space that we observe in the universe today was once compressed together in that primordial, singular moment. The expansion we currently observe is nothing more than a continuation of that primordial, grand expansion. Such an understanding gives rise to the deepest mystery about the origin of all existence. What existed before the Big Bang? This question may prove meaningless, since the very concept of before implies the existence of time, and time, according to existing models, began precisely with the Big Bang. This is akin to trying to find out what is north of the North Pole. Such a question, a priori, assumes the existence of frameworks and coordinates that do not actually exist, making it incorrect. Some modern theories suggest that the Big Bang was preceded by a special period of cosmic inflation, when space expanded at a speed exceeding the speed of light for an extremely short moment. This inflation could have been caused by quantum fluctuations in pre-existing spacetime, but such an explanation only pushes the main mystery one step back. What created the conditions for inflation itself? Other theories hypothesize that the Big Bang was one of many similar events, perhaps occurring within a so-called multiverse, where new universes are constantly being born and evolving. However, even these bold theories must confront the fundamental question: why does anything exist at all? What is the first cause of everything? The phenomenon of space expansion forces us to face the deepest mystery of existence, namely the origin of everything around us. Multiverse theories suggest that our expanding universe may be just one of countless bubbles in an infinite and boundless ocean of spacetime. If our universe originated from the Big Bang, then perhaps other Big Bangs gave rise to other completely unique universes. These hypothetical universes may possess entirely different laws of physics, different values for fundamental constants, and different rates of expansion. In such a worldview, our universe would be like one of many bubbles in an infinite cauldron of boiling water, where new bubbles are continuously forming and growing. This multiverse hypothesis is considered to be perfectly tuned for the formation of stars and galaxies. If there are infinite universes with different expansion rates, then it is statistically inevitable that some of them will possess conditions suitable for the emergence of complexity and the development of life. We, for perfectly natural reasons, find ourselves in one such habitable universe. However, the concept of the multiverse also raises new, equally complex questions regarding expansion. If other universes are expanding at different rates, could they collide with ours? Could the expansion of one universe influence the expansion of another? Could there be regions of spacetime where multiple universes overlap, forming complex interactions? Some theories suggest that the multiverse itself is also expanding, thereby creating infinite space for the formation of new universes. This leads to the concept of a hierarchy of expansions. Our universe expands within a larger multiverse, which, in turn, may expand within an even grander structure. This process may potentially continue forever, with expansions within expansions, extending to infinity. The multiverse hypothesis is currently untestable with existing scientific methods, but it vividly demonstrates how the expansion of space opens up possibilities that significantly expand the boundaries of our imagination. If space itself is capable of expanding, then perhaps the very concept of universe is too limited to encompass the true scale of reality. Such theoretical considerations point to a coming future where continuous expansion can lead to stunning discoveries that will fundamentally change our understanding of being itself. The accelerating expansion of cosmic space is already transforming the fundamental structure of the universe in ways we are only beginning to comprehend. As the rate of expansion increases, the colossal cosmic web of galaxies is relentlessly stretched and torn apart. Grand galaxy clusters, currently barely held together by gravitational forces, will be irrevocably torn apart by expansion in the distant future. The largest and most majestic structures in the universe are already in the process of disintegrating, leaving behind increasingly isolated island universes. This process is absolutely irreversible. Once expansion carries galaxies beyond each other's mutual gravitational influence, they will never be able to reunite. The universe becomes more and more fragmented, with each group of galaxies evolving in complete isolation. Future civilizations will gaze upon a much emptier and more silent sky than we observe today. Acceleration also affects the very flow of time. As space expands at an increasing rate, the redshift of light from distant objects becomes more and more extreme. Light from the most distant galaxies is already shifted into the radio range of the electromagnetic spectrum. Eventually, this light will be shifted to wavelengths exceeding the size of the observable universe itself, making it absolutely impossible to detect. This creates a kind of cosmic censorship. The expansion of space gradually erases all evidence of the Big Bang and subsequent cosmic evolution. Future observers will see a universe that appears static and utterly empty, without any possibility of detecting that it was once filled with billions of galaxies and rich in complex structure. Expansion also changes the very nature of space. As dark energy becomes an increasingly dominant force, the properties of space-time may evolve in completely unpredictable ways. The universe of the future may operate under entirely different rules than the universe we know today. These colossal changes occur slowly by human standards, but they are reshaping the entire cosmos on timescales that are dwarfed by the existence of any civilization. The expansion of space could ultimately become so extreme that it literally tears atoms apart, leading to a final cosmic catastrophe. If dark energy continues to accelerate the expansion, we may be heading towards a scenario called the Big Rip. In this coming future, expansion will reach such a speed that it overcomes all other forces in the universe, including the forces that hold matter together. The universe will literally tear itself apart at the most fundamental level. The Big Rip would unfold in stages. First, galaxy clusters would be torn apart as expansion overcomes gravity. Then, individual galaxies would disintegrate as expansion becomes stronger than the gravitational forces holding them together. Next in line would be solar systems, their planets torn from their stars. Eventually, expansion would become so extreme that it would overcome the electromagnetic forces holding atoms together. Molecules would be shredded. Then, atoms themselves would be pulverized as expansion rips electrons from atomic nuclei. Even atomic nuclei would be torn apart as expansion overcomes the strong nuclear force. In the very last moment, expansion would tear space-time itself apart. The fabric of reality would be stretched beyond its breaking point, creating a universe where distance, time, and causality lose all meaning. The Big Rip would be the ultimate triumph of expansion over all other forces in the universe. This scenario is highly speculative and entirely depends on the future behavior of dark energy, but it vividly illustrates how the expansion of space can lead to consequences that are literally unthinkable for the human mind. The gentle and barely perceptible expansion we observe today may be just the beginning of a process that will ultimately destroy everything we know about reality. The possibility of the Big Rip compels us to recognize the most extreme and dramatic consequences that cosmic expansion can lead to. Even if global expansion doesn't tear the entire universe into tiny fragments, it will inevitably lead to a future that is unimaginably different from what we see today. The most probable scenario is that the expansion process will continue forever, but its speed will gradually decrease. The universe will steadily increase in size and become exponentially emptier, gradually approaching a state known as heat death. This will be a cosmos where expansion has so strongly and irreversibly dispersed all available energy and matter that no interesting events or processes can ever happen again. In such a distant future, the observable universe will significantly shrink in its boundaries, encompassing only our local group of galaxies. All other galaxies will disappear beyond the event horizon, making the universe appear small and static to hypothetical future observers. The cosmic microwave background radiation will be so strongly redshifted into undetectable wavelengths that it will erase the last, even faintest evidence of the Big Bang. Stars will gradually fade one by one, leaving behind only cooled white dwarfs, dense neutron stars, and mysterious black holes. These cosmic remnants will orbit each other in ever-expanding spirals as the ongoing expansion of space relentlessly pulls them apart. Eventually, even these gravitationally bound systems will be separated by the relentless and all-encompassing growth of space itself. The final chapter in the story of the cosmos will be written by black holes, which, according to predictions, will slowly evaporate through Hawking radiation. As they shrink in size, they will release their accumulated energy back into the expanding universe, creating a brief but brilliant burst of activity in an otherwise dead and lifeless cosmos. When the last black hole disappears, the universe will remain utterly empty, except for photons and elementary particles that will endlessly propagate in an ever-expanding space. This heat death scenario represents the ultimate and absolute triumph of expansion over all organization. The universe will become a place where entropy reaches its absolute maximum, where no energy can be extracted to perform any work, and where the very concept of events will lose all meaning. However, even this bleak and joyless future holds profound and unsolved mysteries about the very nature of existence. The expansion of space raises questions before us that are perhaps fundamentally unresolvable, pushing the boundaries of human knowledge to its limits. We can measure the rate of expansion, predict its possible consequences, and even trace its history. But we cannot yet explain why it happens at all or what it ultimately means. The expansion of space appears as one of the fundamental and inherent features of reality, similar to the existence of mass or the relentless flow of time. We can describe it, but we cannot explain why the universe chose to be this way and not some other way. This limitation reveals something important about the deep nature of scientific knowledge. Science is incredibly effective at describing how something functions, but it faces enormous difficulties when it comes to questions of why something exists at all. The expansion of space serves as a vivid example of this fundamental limitation. We can map its many effects with incredible precision, but we are unable to answer the deeper question of why space expands rather than remaining static. Expansion also forces us to confront the astonishing possibility that some questions may be literally unresolvable. If the universe is expanding into nothing, then the question of what lies beyond it becomes utterly meaningless. If the Big Bang was the true beginning of time, then the question of what existed before it is simply impossible to answer. These are not merely limitations of our current knowledge. These may be fundamental and insurmountable limits to what can be known at all. Perhaps the most profound implication is that expansion makes the universe fundamentally mysterious and incomprehensible. We inhabit a cosmos that is much larger than we can observe, older than we can trace its history, and more complex than we can fully understand. The expansion of space has made the universe not just physically larger, but intellectually humbling, forcing us to recognize the limits of our understanding. Such humility can be the greatest of gifts, capable of expanding human consciousness, as it opens up the understanding that reality is truly far more amazing and unimaginable than the mundane experience of our daily existence. The expansion of space inevitably connects us with the deepest mysteries of existence, while simultaneously reducing us to an infinitesimally small quantity in the colossal tapestry of cosmic history. Every single atom that makes up your body was once compressed into a region smaller than a proton at the moment of the grand event known as the Big Bang. The expansion of space has relentlessly stretched the universe for almost 14 billion years, carrying these atoms through complex cosmic evolution until they became an integral part of you. You are, in essence, literally made of expanded space-time, shaped by the very same forces that relentlessly push galaxies apart. This profound connection makes the phenomenon of space expansion truly personal. The growth of the universe is not just some abstract physical process. It is the fundamental mechanism by which the primordial materials of existence were transformed into the incredible complexity we observe today. Without the process of expansion, neither galaxies, nor stars, nor planets, nor life itself could exist. However, expansion also vividly demonstrates how infinitesimally small we are on the vast cosmic scale. The observable universe contains at least 2 trillion galaxies, each containing billions of stars. The actual universe is likely significantly larger, perhaps even infinite. Expansion constantly opens up new regions of space that dwarf everything we have ever known or could imagine. This creates a profound internal tension between significance and insignificance. We are significant because we are an integral part of cosmic history, products of the very same expansion that shapes the universe. But we are insignificant because expansion reveals a universe so vast that our entire observable region is just a tiny sample of a much larger reality. Perhaps this tension itself holds deep meaning. Perhaps the expansion of space is the universe's way of creating both connection and perspective, showing us our true place in cosmic history, while simultaneously revealing how much more there is to discover. The expansion of space makes us simultaneously everything and nothing, inextricably linked to the cosmos and yet lost in its boundless expanses. The mystery of cosmic expansion will likely outlive our species, our planet, and our sun, continuing to puzzle minds we cannot even imagine today. Long after Earth is swallowed by the expanding sun, long after our galaxy merges with the Andromeda Galaxy, long after the last stars fade, the expansion of space will continue. It will be the most enduring feature of reality, outliving every structure it helped create. Future forms of intelligence, if they exist, will still be trying to understand why space expands and what it truly means. These future thinkers will have advantages we cannot even imagine today. Perhaps they will have access to regions of space that we can never observe. Perhaps they will comprehend the true nature of dark energy and the quantum structure of space-time. Perhaps they will even develop technologies that allow them to manipulate expansion itself. But they will also face limitations we cannot foresee. Expansion will carry much of the universe beyond their horizon, making it even more difficult to study the cosmos as a whole. Evidence of the Big Bang will be shifted to undetectable wavelengths. The universe will appear smaller and more mysterious than it does to us. This creates a kind of cosmic irony. The expansion that allows for the existence of complex life also ensures that the universe becomes increasingly difficult to understand. Each generation of observers will see less of the cosmos than the previous generation, making the mystery of expansion deeper, not shallower. Perhaps this is quite fitting. The cosmic expansion of space represents a phenomenon that most fully approaches the definition of a truly fundamental characteristic of the cosmos. It is a phenomenon certainly worthy of preserving its mysterious nature, constantly challenging any form of intelligent life that arises during the grand cosmic process that it itself makes possible. The expansion of the cosmos will continue to generate insoluble mysteries long after humanity ceases its attempts to find exhaustive answers to them. Regardless of whether this expansion is destined to last infinitely or if it will eventually reverse, it has already inscribed the most significant chapter in the annals of all existence. It is the expansion of space that enabled the universe to evolve from its initial extremely hot and dense state to the abundant and multifaceted cosmos that humanity inhabits today. If expansion had not occurred, the universe would have invariably remained in a state of uniform plasma, whose temperature and density would have been excessively high for atoms to form. If, on the other hand, expansion had been too intense, the cosmos would have become too cold and diffuse, preventing the condensation and formation of star systems and galaxies. Thus, the rate of expansion that scientists observe today proved to be perfectly balanced, facilitating the emergence and development of complex structures. Such precise tuning gives rise to the deepest philosophical and scientific questions regarding the essence of being. Why does the universe expand at precisely the rate that proved critically important for the emergence and stable existence of stars, planetary systems, and ultimately, life itself? Is this merely an incredible cosmic coincidence? Or does this circumstance point to something more fundamental in the nature of the cosmos? Perhaps humanity inhabits only one of countless potential universes, which was simply fortunate enough to possess an ideally suited expansion rate. The phenomenon of expansion also prompts reflections on the ultimate purpose and profound significance of existence. If the cosmos is steadily moving towards a state of heat death or a big rip, then everything humanity creates will ultimately be doomed to destruction. Does this make human existence meaningless and futile? Or perhaps the awareness of this finiteness, on the contrary, gives each moment even greater value, emphasizing its unique but transient nature. Perhaps the most significant lesson that cosmic expansion teaches us is that human existence falls within a relatively brief period when the universe appears particularly fascinating. Humans live in an era when stellar systems are actively forming, when galaxies are observable, and when the cosmic microwave background radiation is still detectable. This is truly an exceptional segment in cosmic chronology, and humanity is incredibly fortunate to be an active part of it. The expansion of space has shaped a universe that appears to us as both magnificent and terrifying, deeply meaningful and paradoxically absurd, quite comprehensible and yet immeasurably mysterious. It has bestowed upon humanity a cosmos that rightly deserves both the deepest admiration and reverential awe. Thus, the expansion of space is the culminating manifestation of the universe's creative power, continuously generating room for the emergence of countless new possibilities, many of which humanity is not yet even capable of imagining. At this very moment, as the reader finishes contemplating the concept of cosmic expansion, space continues to expand at a truly dizzying speed. In this very instant, entirely new regions of the space-time continuum are emerging. Hitherto unknown possibilities are opening up, and new, as yet unsolved mysteries are coming to light. The universe is literally creating itself, expanding and tirelessly recording the chronicle of its existence, literally 1 cubic inch at a time. This continuous, endless creation represents the most outstanding and astonishing characteristic of the expansion process. The essence of the process is not merely the mundane increase in the volume of space. Far more important is that space is gaining an ever greater capacity to accommodate complexity, form diverse structures, and generate unpredictable phenomena. Each newly emerging region of the cosmos serves as a kind of blank canvas for further cosmic evolution, on which stars, galaxies, and perhaps even forms of intelligent life that humanity cannot yet imagine can be depicted. Among other things, expansion embodies the universe's deepest commitment to continuous exploration and self-discovery. Instead of remaining in a static and easily predictable state, the cosmos has consciously chosen a path of growth, transformation, and striving to become something significantly greater than it was before. This is by no means a passive course of events, but rather an active decision of reality itself, aimed at embracing uncertainty and boundless possibilities. Humanity is an integral part of this grand creative process. Its existence represents both a result of cosmic expansion and an active participant in it. Humanity serves as a kind of instrument through which the universe seeks to comprehend itself, to ask questions about its own nature, and to express admiration for its own boundless creative potential. It is thanks to humanity that the expanding cosmos has gained the ability for self-contemplation and understanding of its own continuous expansion. Such a state of affairs makes humanity exceptionally privileged witnesses to a grand cosmic evolution. The existence of our species falls within a period when the cosmos is still young enough to retain memories of its origins, but already mature enough to give rise to intelligent life. Humans are capable of perceiving the cosmic microwave background radiation, studying distant galaxies, and thus reconstructing the full picture of how cosmic expansion shaped all known reality. It is the incessant expansion of the spatial fabric of the universe that became the foundation for our emergence, and we, in turn, were able to comprehend and understand the profound mystery of this phenomenon. The cosmic expansion of space is truly the greatest illusion of the universe, capable of creating something infinitely vast from a tiny point, smaller than an atom. Humanity has embarked on an amazing intellectual journey through a discovery that fundamentally changed our perception of reality. We have thoroughly explored the astonishing truth that the very fabric of space is continuously increasing in volume, and we have come face to face with the deepest mystery. What does it truly mean for all existence to expand into absolute emptiness? We have witnessed how this expansion created the necessary preconditions for the emergence of countless stars, grand galaxies, and ultimately, consciousness itself. It continues to actively transform the cosmos on timescales that immeasurably exceed the duration of all human existence. The most profound insight gained during our research is the realization that the question, "What is the universe expanding into?" vividly demonstrates the fundamental limitations of human language and thought when confronted with the most intimate mysteries of being. We are creatures evolved to survive in a world dominated by concepts of boundaries and containers. And now we are trying to comprehend a reality that completely transcends these familiar categories. However, this apparent limitation is also an invaluable gift. The continuous expansion of space encourages us to expand our own minds, just as it stretches the very fabric of reality. This process stimulates us to think beyond ordinary human experience, to embrace mystery as an inherent and fundamental feature of the cosmos, and to seek meaning in a universe that turns out to be far more bizarre and astonishing than we could ever have imagined. Looking into the distant future, when expansion carries many distant galaxies beyond our observable horizon, we can still find solace in the realization that our existence falls within a truly remarkable moment in cosmic history. We are direct witnesses to the universe's greatest creative act, the continuous expansion of the spatial fabric itself. Through careful study of this phenomenon of expansion, humanity, in essence, participates in the grand attempt of the cosmos itself to comprehend its own nature. The expansion of space still remains the highest frontier of human knowledge, an unsolved mystery that will continue to inspire wonder and exploration long after our species joins the great cosmic dance of expansion and transformation.